Good morning, Astronomy 1010, and welcome to our first lecture after the midterm exam, which you guys just beasted out on Monday and maybe even a little bit on Tuesday. My midterm grades are due today, so I'm going to post a sort of progress report of how your grade is looking at this point in the class. So this is a good time to sort of evaluate what you've done and how things have been going. Because I know that grades are important to students, I will take a moment to explain my grading system to you guys so you can understand how I will be computing the midterm. I'm getting some autofocus issues here, so I got to open up the Logitech capture. We don't want any trouble today. Sorry about this. Come on, you stupid. Everything is so slow. Okay, so autofocus is now off, and that means it should behave. Okay. Remember that the idea behind this course is that your grade is a combination of 1/4 of each of these categories. So 25% of your grade comes from homework, one of which we're going to be doing today. We'll be doing homework 6 today. 25% comes from your lab work, which we usually do on Mondays. I think it's time for a fresh one. It's time for my last good fresh marker here. 25% comes from the midterm, which you just completed, and 25% comes from the final. Now, up to now, we've done 5 homeworks and 5 labs. So your homework percentage, 5 times 25 points is what, 125 points? So you'll have some number of points out of 125. For lab, each lab is worth 10 points. So you'll get something out of 50 points. And then the midterm was out of 100 points. And these are going to give us 3 percentages. I want you guys to imagine, for the sake of argument, hello, Enrique. It's nice to see your face for a change. And that little pooch there. Look at that little pooch you got. What's that guy's name?
This is Ted.
All right, Ted. Ted, welcome to the class.
Thank you.
I want to give you guys a sense of how I would compute a grade if you were a student who has done every homework, every lab, and then let's say you got a 50% on the test, okay? Normally, one wouldn't think of getting a 50 on a test as a good grade, but you're going to see that in this class, a 50 on the test could be a reasonably good grade. But let's pretend that you're a great student who always comes to lecture and always does labs and homeworks. Most of you do that. You would have a roughly 100% for your homework, and you would have a 100% for your lab. And let's say that you got a 50 on your test, so you have a 50%. Now, in the final exam, once we do the final exam, each of these will be averaged 1/4 weighting, so I would add them up and divide by 4. But I cannot do that at this point because I don't know what you're going to get on the final. That's up to you. That's not up to me. I am going to assume, for the purpose of calculating your midterm grade, that you will get the exact same score on your final that you did on the midterm. And that way I can take a reasonable average with an equal weighting of exam stuff and homework stuff. So I'm going to assume that if you got a 50 on the midterm, you'll also get a 50 on the final. And then I would take the average. Let's think about the average of these scores. 1, 2, 3. That's a 3 divided by 4 is a 75%. And this would be hypothetical student John Doe's grade, 75%. But what does 75% mean to me? Well, I apply a curve for my class that goes something roughly like this. I peg B- to a 65%, and then it goes in roughly 5-point increments from there. A B is 70%. A B plus is a 75%. A minus is an 80%. A is anything that's over 80%. I think that's a very generous scale on my part. I know I'm the best, right? Okay, so also C plus is anything over a 60%. There is no C minus at CCRI, so I guess that means I can extend C all the way down to 50%. That ought to help some people in this class. After that, we get into D territory. D plus is 45%. And if you're getting less than 45% in this, or 40% in this class, you can consider yourself to be failing. Luckily, hardly anyone is in this case. You have to really be a major flake to get into this category. You have to consistently not turn in homeworks and labs. Okay, notice that my hypothetical student who scored a 50% on the test is still earning a B plus for this class. And let's analyze why John Doe is earning a B plus. They're earning a B plus because they did all their homeworks and all their labs. So the test can't hurt them that much. Wow, I guess it's a really good idea to do all your homeworks and labs, isn't it, guys? I guess that's the moral of this story. Okay, does anyone have any questions about that? Maybe something that I could explain a little better, or maybe you've got an issue that I didn't address? What y'all thinking? Jake likes it. In any case, I want to give you guys a sense of how I'll be grading, how I'm going to compute your midterm grade. So I'll be doing that today after the class. Did you guys find the test easy or hard? How do we feel? Not easy, Enrique? Well, I guess I really
challenging.
Yeah, I designed it to be kind of a slog. I think the moral of the story is if we do our homeworks and labs, we're already kind of prepared for the tests because we've already practiced punching in with our calculators. That doesn't mean we're going to be awesome and get 100%. I don't design my tests for everyone to get 100%. I design it to be hard. Just see what you guys can do.
Honestly, while I was taking the exam, Professor, I felt like it was like a little easy, but when you like go down into like the questions and stuff, it definitely felt harder going down.
As you get into more of those math questions.
Final answer.
Also, keep in mind, guys, that this stuff is still pretty fresh to you, right? You've only been using the calculator and punching stuff in for about 4 or 5 weeks. So you're still pretty raw. I'm hoping that as the semester goes on, the class will be a little more easier because you know the drill. You already know how to punch things into your your calculator. So you won't be fighting the calculator. You'll just be fighting the concepts and thinking about things. We'll see if that happens. Okay. If there are no other questions about grading policy, then look for your midterm projection today to see how you're doing. And you can always try to calculate it yourself based on how many homeworks you've turned in. You should be able to look at your scores right there in Blackboard. All right. So last time we left off talking a little bit about light. And light was featured in a little bit on your exam. Tell me about the electromagnetic spectrum, guys. While I'm erasing here, what do you know about the electromagnetic spectrum? Do you know anything about the electromagnetic spectrum?
I do. I know a little bit.
All right. Tell me.
So you have like gamma rays, X-rays, and some of those fit in colors based off of
Wait, there's gamma rays, X-rays. What else is there?
Ultraviolet.
Ultraviolet.
Infrared.
Visible light comes between UV.
Oh yeah, that.
Right. Let's not forget about the visible spectrum, right? What are the order of the colors? Do you know the order of the colors?
Oh, Roy G. Biv. So it'd be.
Right. What if we do it in the other direction? Because this is going with increasing wavelength here. This is increasing.
Oh, so it'd be violet, indigo blue, green, yellow, orange.
And then red.
And red.
I call that VIBGYOR. VibGyor is the opposite of Roy G. Biv. I don't know about you guys, but I like the idea of wavelength getting longer towards the right. I could flip this whole thing around, and some astronomers do that. But since wavelength is a key concept in this class, I like to think of it going this direction. So then there's infrared, and lastly, there's radio. And you guys are supposed to know about these bands of the electromagnetic spectrum, right? Now, today I want to talk about how we can use light in different bands of the electromagnetic spectrum to analyze the sort of matter that is producing that light. If you think about it, we're not quite there to the point where we can get inside our Millennium Falcon or the Starship Enterprise and travel to nearby stars and take a peek and see what's going out there. I'm mad at myself that I was born in this time period. Maybe if we were born 300 years in the future, we'd be able to actually pilot our own spaceship to the stars, and that would be a pretty badass situation. But I'm not there yet. So if I want to know about stars, if I want to know about planets, all I can do is really analyze the light from those stars and planets. And so that means this telescope is my vehicle for exploring the stars. I'm going to gather some photons with this lens. I'm going to either analyze it with my eye, or if I'm very clever, if I'm a very clever person, I will use a prism, or I will use a diffraction grating. A diffraction grating is kind of like the thing that's on the back of a CD, a compact disc. It can make a rainbow with a diffraction grating. This is also a diffraction grating. This piece of film has these finely etched lines that will separate light into its component wavelengths. Let's take the spectrum of, what do I have that's of a match? How about that? I love teaching from home because I can do all these sorts of dangerous things they would never let me do at CCRI. And today I'm going to light a match. Okay, that's my dangerous thing. All right. So what do you think the spectrum of this match is going to look like? Now just look at one of those, ooh, there we go. Just, it looks like I can see a rainbow there. I can see red, orange, blue. The spectrum of a match turns out to be a rainbow. It might not have been obvious what you were looking at there, so let me show it to you. The spectrum of a match basically looks like, this. It's the same as the spectrum of a light bulb. It's called the continuous visible spectrum, or VibGyor: violet, indigo, blue, green, yellow, orange, red. These are the colors of light that your eyeballs are sensitive to. Now, did we talk about what the word spectrum means? I don't know if we actually got to that or not. Did I define spectrum in one of our notes there?
I don't think so.
Okay, then I think because today is about the art of spectroscopy. What do we mean by a spectrum?
Oh, wait, no, you did.
What did I say about it then?
It breaks light apart into its component colors.
Right. Now, when I took the spectrum of that match, I was breaking the visible light into its component colors because that's what your eyeballs see, visible light, and that's what your camera sees. But of course, it's possible to design cameras that see at other wavelengths of light. You can build cameras that see into the infrared or the radio, and astronomers actually tend to work in one of the bands of the electromagnetic spectrum. Like when I was a student, I worked for a bunch of astronomers who worked only in the infrared band and only in the radio band. They didn't even give a shit about visible light. That wasn't, in fact, one of my professors said to me once, he said, optical astronomy, visible astronomy sucks because you can't see anything with it. In other words, he was an astronomer who wouldn't even look with his eye through a telescope because he felt like it was a waste of time. That's how crazy some of these people are, okay? Some of us people are, I guess. There are reasons why you'd want to work only in a rate. And by the way, so what would that look like? Let's take a peek. If we go to Mr. Internet here, There are many cool radio telescopes around the world. One that comes to mind is the Effelsberg 100-meter telescope. This is a radio telescope that scans the skies only, where's a cool picture of this thing? Maybe here. It only looks at radio wavelengths. You can see certain things in radio wavelengths that you can't see at other wavelengths of the electromagnetic spectrum. Radio telescopes are cool because you can peer into the hearts of galaxies. So if you guys saw in the news recently that they took a picture of a supermassive black hole, they did that using many of the Earth's most famous radio telescopes. Okay, so we know what a spectrum is. And we know that when we break light apart into different component colors, okay, let me say one other thing too. This is just a kind of reminder. In the electromagnetic spectrum, there is a relationship between wavelength, frequency, and energy. Wavelength increases to the right, but frequency and energy, they get stronger to the left. So radio wavelengths are long photons. They have a very long distance from crest to crest. And gamma rays are very short wavelength photons. They have a very short wavelength from crest to crest. But it turns out that the shorter your wavelength, the higher your energy. Radio waves pass harmlessly through your body. You see this cell phone here? This is actually a sophisticated radio transmitter. And when I hold this thing up to my ear, I'm actually shooting radio waves right through my brain. Does that hurt me? No, because the wavelengths are long and the energy is very low. There's not enough energy to disrupt my brain function or harm me in any way. However, at the shortest wavelengths, the energies are very high, and I certainly wouldn't be holding this thing up to my skull if it was a gamma ray emitter, because then I would turn my brain into a Teenage Mutant Ninja Turtle, okay? I might get superpowers, or I'd probably just get cancer and die. Anyways, gamma rays are harmful. And one of the ways we know that is because there's a relationship between these quantities. I made you do this on the test. The speed of light is wavelength times frequency. The energy is Planck's constant times the frequency. And the energy can also be written as hc over lambda. Do you guys see how energy is on top and wavelength is on the bottom? Energy is inversely proportional to wavelength. And I'm going to explain what that means for people who don't speak math. And I'm going to use symbolic colors. Long wavelength, equals low energy. And where's the marker here? I just saw you, you bastard. Well, I wanted to, oh, there's purple. Short wavelength equals high energy. I did something kind of clever there, but I wonder if any of you noticed it. Did you guys notice the colors that I chose? Why did I choose these two colors? I was trying to be symbolic there. I was trying to be clever. Why did I choose red? Why did I choose violet?
Because it represents, like, red is at the end and violet is at the beginning.
Right, violet's a short wavelength light. Red is long wavelength, right? Even though we cannot see with our eyes infrared and radio waves, sometimes astronomers call this the red end of the spectrum. Now, you think they would call this end the purple end? That would make sense. But because people are strange and weird and they do screwy things, they call this instead the blue end of the spectrum. It turns out that eyeballs are not really sensitive to purple light. Purple light is kind of hard to see. When I'm at the telescope and I look at purple wavelengths of light, they appear ghost-like. They're almost like transparent. Your eyes are more sensitive to blue than purple. Okay, so I can go and I can find light and I can do different things with it. And I want to, before I go any further, I want to show you guys a picture from your book. And I want to talk about ways that light can interact with matter. So you can think about that for a second. Oh, actually, guys, there's a couple of different things I want to do today. I want to talk a little bit about the inverse square law. Yeah. Okay. Before I talk about ways that, sorry, I'm having a little bit of neuroses here. I'm going to talk about ways that light can interact with matter, which was I was going to do, but I need to talk about the inverse square law after that. I don't think I gave that enough treatment earlier on. So I just want you to look at this picture for a second, and I want you to just think about things, okay? Light can interact with matter in a variety of different ways. Here is the sun. The sun is an emitter of light, meaning light is actually being produced at the sun, and photons are coming off of it. One of my goals to do with you today is to talk about how objects emit light and how we can analyze their composition based on the type of light that they emit. So let's think about things that definitely produce their own light. The sun would be an example, right? This light bulb is an emitter of light. What else emits light? Can you think of anything besides the sun and light bulbs that emit light? No?
Fire.
Fire emits light. Good, Enrique. In fact, that's what I was just doing a moment ago when I set this match ablaze. We analyzed the light from the match. Also, other ideas, lightning bolts, glowworms, lots of things emit light. Neon signs. Okay. Once the light is emitted, we usually see not the glowing, well, we can look at a light bulb and we can see light, but when light strikes the ground, two different things happen. The ground can absorb light, and the ground can also scatter light. When you scatter light off of a surface, light bounces all around in all directions. For instance, consider the fact that I can take my red marker and I can put a red dot here on the board. That red dot, students, is not an emitter of light, and yet you can see light from this red dot. Light that's coming from my overhead lamps and from the windows in my room are bouncing off of that red dot. The red dot must be absorbing violet, indigo, blue, green, yellow, and orange, but it backscatters red photons in all these different directions. Some of those red photons leave the board and come right into the camera, and then they go into your eyeballs. So you see most things in nature because they're scattered light. My face, for instance, I'm not glowing. Well, not at visible wavelengths anyways. You can see light on, you can see my face because photons scatter off my nose and my eyes and they bounce into the camera. Light can also be transmitted. It can pass through glass. Light can be reflected from mirrors. There's lots of complicated ways in which light can interact with matter. And over time, I want to talk to you about those different ways and talk to you about the physics, the underlying physics of what's happening. For instance, if the ground can absorb sunlight, it must mean that the atoms themselves are capturing those photons. And of course, that warms up the atoms, and therefore it warms up the ground. But first, let's talk about light bulbs for a minute. Okay, so let's talk about how this here light bulb generates light. You know, oftentimes we talk differently about light when we talk about it in a macroscopic sense versus a microscopic sense. For instance, you'll remember that in the microscopic domain, in the world of the small, light is comprised of photons. And photons are like tiny packets of light. Except I'm going to cross out tiny because sometimes they're big packets of light, like radio waves. And when we talk about light in a macroscopic sense, we often talk about a beam of light. Sorry. We'll talk about a beam of light, or we'll talk about rays of light, or we might just talk about the total luminosity output. And that's sort of what I want to get into now. So we'll take a light bulb, we'll switch it on, and when we do this, light will be emitted from it in all directions. So now I'm going to take a look at this light bulb from a macroscopic sense, okay? Here come the photons streaming out from my light bulb. They radiate in all directions, coming from the filament. Actually, the light bulb isn't perfectly isotropic because the light cannot travel through this little metal opaque thing, but they're basically traveling in all of the directions. If I wanted to measure the amount of energy that comes out of a light bulb, I could use a fancy device called an integrating sphere. An integrating sphere looks like this. It's a kind of fancy machine where you have an Edison socket and you put in a light bulb, you close up the sphere, and then this computer will read the total amount of energy coming from the bulb. Now, at first, you'd put in a brand new light bulb and you'd turn it on, and energy would begin to flow out of the bulb into all directions. But you can't really talk about the energy that comes out of a bulb because energy is constantly coming out of the bulb. It's floating out this way, it's flowing out that way. And in kind of the same way that when you stand next to a river, water is constantly flowing by a river. You can't really ask how much water is in a river because that question does not make sense. You can only ask how much water flows by in a day, how much water flows by in an hour. And there is a similar concept related to energy and light. It's called power or luminosity. Power and luminosity, they both mean the exact same thing. Power and luminosity mean energy per unit time. You can think of them as an energy flow. Do you guys remember what the MKS units for energy and time are? How do I measure energy in the MKS system? It's always good to make sure you guys know some things, you know?
Is it joules?
And how do I measure time in the MKS system?
Meters per second squared?
That's acceleration.
Oh.
Just time. Think about it, Jake. Time.
Seconds?
Yes.
Okay.
And do you know what a joule per second is?
I did.
The units of luminosity are called the watt. 1 watt is 1 joule per second. What does luminosity mean? It's the energy flow in all directions. And another concept is that it's usually a fixed number for a given object. Hey guys, I don't know if you can tell, but I am like sweating my pants off here. But I don't mean literally. I need to turn the heat down in my apartment because I'm dying. 1 second. Okay, thank you. What do I mean by it's a fixed number for a given object? Well, let me show you such an object. This here light bulb. And this here light bulb, if you look at the writing, let's go to my Logitech thing and I'll adjust my focus to like 31 or something. Okay, now you should be able to see the writing on this thing. There you go. It's 60 watts. If you look there. This light bulb pumps out a luminosity, or it uses a luminosity or a power of 60 watts. Okay? And that tells me how much energy is flowing from the bulb in all directions. Something to keep in mind is that this light bulb is 60 watts, whether I plug it in over here, whether I plug it in there, or whether I plug it in on the other side of the galaxy. It's 60 watts because it's a fixed property of the bulb itself. Let's talk about another famous luminosity, the luminosity of the sun. May I erase this, students?
No, I'm not done.
Okay.
Same here.
Let's grab that. Can you let me know when you are
Yeah.
done?
I'm all
Mhm.
set.
I'm still writing.
Okay, Cam, let me know when you're good.
Go ahead and erase it. I'm all set.
Thank you. Okay, so let's talk about the luminosity of the sun. The luminosity of the sun, and by the way, that little circle with a dot in it, that's the astrological symbol for sun. So astronomers sometimes represent the sun with a little circle and a dot. The luminosity of the sun is a fixed constant, and it has a value of 4 times 10 to the 26 watts. That's a lot of energy flowing from the sun in 1 second. I want to talk to you guys about a cool hypothetical concept from science fiction. As you guys probably know, I am a big sci-fi nerd. That comes with the territory of being an astronomer. Suppose I could take a giant integrating sphere like this thing here, and I could cover the entire sun with it. I would be able to capture all the energy that's radiating out of the sun every second. And this hypothetical concept is called a Dyson Sphere. It's imagined that in a future advanced civilization that occupies Earth, we will become so technologically sophisticated that we will be able to cover the sun with a solar panel bag, and like cosmic ticks, we will suck energy off of our star and use it to power our toasters and our microwaves and our spaceships. Cool concept, bro. Okay, suppose I could capture 1 second of total sunlight. Can you guys tell me how much energy I would capture? So we build a Dyson sphere. And the question I'm asking the class is, if I captured 1 second of total sunlight in all directions, my question is, how much energy would I get? Can you guys answer that question? I need you guys to work with me here. How much energy would I get if I captured 1 second of total sunlight from a Dyson sphere? The answer should be obvious.
Would it be 4 times 10 to the 26 joules? Oh wait,
Yes.
no.
Yes. No. Yes, Frank. That is it. You see, my friends, Frank understands the difference between energy and luminosity. If you had said 4 times 10 to the 26 watts, I would have scolded you. Watts are a unit of power or luminosity. But because watts are joules per second, if I capture 1 second of sunlight, I would have an energy of 4 times 10 to the 26 joules. Very good, Frank. That was a question that was about units, not about math, okay? Okay, what about the United States? You know, one of the photographs that I enjoy showing students because it's beautiful and cool is a picture of the United States at night from, is it from NOAA? And if you look at a picture of the United States at night, you really start to understand why Rhode Island is actually a bad place to do astronomy. It's because of light pollution. So, of course, let's get my annotate tool out. You are here, right? That's where you are. And you can see that this is a pretty shitty place to do astronomy because all of that light blots out your view of the sky. Now, I was lucky enough to go to college in Tucson, Arizona. Even though I'm from Rhode Island, I went to school out here. And I'm guessing that's Phoenix. I'm guessing here. I'm not 100% sure. And I'm guessing that's Tucson. Compared to Rhode Island, the deserts of Tucson are actually pretty dark. And that's why it's one of the world's best places to do astronomy, because the air is dry and you have very few rainy days. And the skies, as you can see, are actually quite dark out here in comparison to Rhode Island. Now, there are some other dark places in the United States. You might say, hey, why don't I build a telescope up there? The answer is because those places are dark, but they're also wet. And you don't want to spend $1 billion building a telescope if it's going to rain half the time. Tucson is both dark and dry, which makes it a great place for astronomy. Over here, not such a great place for astronomy. That's why you see very few giant massive telescopes on the East Coast. Okay, so this entire country requires energy. Look at all of those street lamps we have to power so that we can pollute the nighttime sky. Think about all the Nintendos and the microwaves and the electrically powered remote control drones. The entire United States in 1 year uses 10 to the 20 joules. That is the power consumption of the US. We use 1 times 10 to the 20 joules per year. Joules per year is a power because it's an energy per unit time, but that's not watts. Okay, class, clearly, Frank realizes that we would capture more energy in 1 second from the sun than we would, that's more energy than the United States uses an entire year. Frank, can you tell me how many years I could power the United States if I could collect 1 second of total sunlight? How would I do that?
I think it would be like.
Yes.
Would we have? I think we would have to do like a. Oh wait, we would have to divide.
Yes.
Divide the joule. Yeah.
Let's do that together, nice and slow, Frank. But Frank's seeing that he has to divide this number by that number. 4 times 10 to the 26 joules divided by 1 times 10 to the 20 joules per year. Frank, I bet you could do this in your head. Let's first divide the lead digits. 4 divided by 1. What do we get there?
1. No, wait, 4.
4, right? Times 10. Do you know what to do with the exponents when you're dividing them?
You minus them, which would be 6.
And what are my final units here?
It would be year.
Right, because joules cancel with joules. And then 1 over years gives you years. How many years is that, Frank? In plain English.
Would it be 4 million years?
Right. So what's the point that I'm trying to make? I've got my Dyson Sphere, right? And I want to power the US. If I could capture 1 second of total sunlight, how long could I power the United States of America? No tricks.
Like, you could probably power it by the time like our grandchildren has grandchildren.
Right. For
4 million
4
years.
million years. Could you imagine not paying the electricity bill for 4 million years? That would actually work for me because I owe National Grid a little bit of back pay, if you know what I'm saying. The summer hasn't been good to me. Okay, so why haven't we done that? That sounds like a good idea. So where's my Dyson Sphere? This picture explains why we haven't done that. Why can't I capture all the light from the sun?
Because of Earth's rotation around the sun.
But not even its rotation, Frank. Even if it didn't rotate, we wouldn't capture all of that light, right? Because we can only capture a tiny cone of light. We can only capture those photons which actually make it over to Earth, correct? Most of the light from the sun we do not get to capture. Most of the sun's rays actually travel into outer space so that aliens can see our sun as a little star twinkling on their sky. Most of those photons are just lost to outer space. And this is a point that I'm trying to make. The sun might have a luminosity, which is its total light output in all directions, but you do not capture all of that light. You capture a much smaller amount of light called the brightness. And let me show you a picture of what I mean by that. When we go about capturing light, come on, you stupid. We capture some cone of light that splashes over a detector, which might be a lens or a CCD camera or an eyeball. We don't capture in general, our eyes don't capture all the rays of light coming out of a bulb. We only capture those rays which hit our eyeball or those rays which hit the earth. And that concept is called brightness. So let's do a couple of notes on that here. Introducing two concepts that should be contrasted against one another. There is luminosity, and that's the light output in all directions. It's measured in units of watts, and it is a fixed number for a particular object. And now I'd like to introduce versus brightness. Brightness is how much light you collect with, choose your favorite detection system. It could be your eye, it could be a solar panel, which might be the easiest way to think about it. I can't spell solar panel right now. Or it could be with your telescope. Or it could be with your camera. Or it could be with your, I don't know, cybernetic eye or something. Brightness is not fixed. It depends on distance. And it has units of watts per meter squared. And usually, oh, here's another thing about brightness. Brightness is luminosity divided by the area over which the light is being splashed. Usually the concept is you have a light bulb. We're going to focus on some cone of light. And the area is the area of your square panel over which the light is shining. So my 3D skills my 3D drawing skills are kind of sucky. But imagine I have a cone of blue light, and the brightness is how much light is just coming through this square meter panel, all right? It's how many watts you get per square meter. Now, if brightness is luminosity divided by area, I can combine these two concepts to come up with a very famous formula. I want to give you guys a minute to catch up on the notes. It looks like Cam is still writing. Cam, Andrew, let me know when you guys are ready to move on, because I need more board space here. Cam's good. Andrew?
I'm still working on it.
Okay.
I'm all set.
Okay. So I want to introduce a famous formula. A famous formula known as the inverse square law. It's basically how we calculate the brightness of objects. And the idea is you have a star with some luminosity that's leaving in all directions, and it's surrounded by a big giant sphere over which the light is being splashed. And we're going to ask if the sphere has a radius r, or you could think of it as a distance d, how much light, how many watts per square meter are going to splash through one solar panel some distance d away? And there's two versions. Let me just, I tried to draw a picture there, but there's a better picture in my notes. It's just more elegant. So this is the idea. Here in this picture, you can see that the sun's luminosity, all 4 times 10 to the 26 watts, are splashing over the entire sphere. But if you ask not how many watts are coming over the whole sphere, but if you ask how many watts are coming through this one square panel, the amount of light will change depending on whether you're 1 AU, 2 AU, or 3 AU away from the sun. Because as a beam of light travels through space, it keeps spreading over a bigger and bigger sphere. So the light kind of gets weaker or diluted. The $10 word is attenuated. A beam of light attenuates and gets weaker as it travels through space. There's 2 versions of the inverse square law, and I want you to write them both down. They kind of mean the same thing. So version 1 is brightness equals luminosity over 4 pi r squared. That's when we think of this as the radius of a star. And then there's version 2, which is brightness equals luminosity over 4 pi d squared. Both of these formulas are called the inverse square law. They're key formulas in astronomy. This one helps you find the brightness at the surface of a star This one helps you find the brightness of a star on your sky. These are concepts we should have already covered, but I did cover them briefly, but I didn't do a good job of it. Today I'm trying to do a good job of it. Could you let me know when you're done? Because I want to try a sample problem next. I'm taking a long time to do this, but it's important. Cam, can I erase? Andrew? Enrique?
I'm not done yet.
Oh, Enrique's good. Okay, hurry, because I have so many things to do today for us to cover our homework. That's a D, by the way.
I'm all set.
Thank you. All right, guys, do we want to try a sample problem where we punch some stuff in? Let's just do it quickly. Here's a question. Find the brightness of the sun at 1 astronomical unit from Earth, okay? We know that the luminosity of the sun is 4 times 10 to the 26 watts. We know the distance of the sun is 1 AU. That's how far away we are when we're looking at it, which is 150 million kilometers. Can you guys quickly tell me how many meters that is? How many meters would that be? No?
150 times 10 to the 9th.
That's right. You add 3 zeros to get to meters. Okay. We need this to calculate the brightness. We need meters. So the brightness is luminosity over 4 pi d squared. The luminosity is 4 times 10 to the 26 watts over 4 over pi over 150 billion meters squared. Guys, I think it's a good idea if you try to punch that into your calculator, because I know many of you are going to screw this up. So punch it up. Punch it up and tell me what you get. Let's do something. I bet not everybody gets it right the first time. Joel got it. Bella got it. Jake did not get it. Jake, you made a mistake. That's okay, buddy. That's why we're learning, right? Jake, if I didn't think anyone was going to make a mistake, I wouldn't have done this problem. How about Cam, Enrique? What are you guys getting? Andrew, what are you getting? Sorry, Frank. Sorry, Enrique. No good. Okay, can I tell you what you guys did wrong? I already know what you did.
Wait, I know what it is.
What'd you do, Andrew?
That times down there is supposed to be division.
Right, you write times, but Enrique and Jake, listen to me. You have to divide by 4. You have to divide by pi, and you have to divide by 150 exp9 squared. Here, just watch me and let's do it together, okay? Clear out. Everyone, let's do it together. 4 exp26. Now watch me. Divide by 4. Divide by pi. Then divide by 150 exp9. We got to square that, which is what I think you got. Enrique, you might have just forgotten to hit equals because you hit square, but then if you hit equals, you can see your true answer. How should I round this? Okay, there we go, Cam. Enrique, good. Enrique, I think you just forgot to hit equals maybe or something. Okay. Jake, did you get it this time? Okay, so how should I round that? Joel, what do you think?
1415 watts
No,
per
that's too
meter
many
squared.
figs. You can keep 2 at best.
1400
1400. And Bella, what are the units?
meters.
You got watts up top. You got meters in the bottom with a square.
Okay, so it's watts per meter square, right?
That's right. This is a number that's known in science and engineering by, this is a famous number. It's called the solar irradiance. Very famous number in engineering. How big is a meter? How big is a square meter? If you think about it, guys, this chalkboard that I write on is approximately, let's move the camera here. This chalkboard is pretty close to 1 square meter. So I can't even hold a square meter in front of this camera. It's too big, okay? It's bigger than a microwave box. It's like almost the size of a refrigerator box. So that means I could power 1,400 watt light bulbs with a 1 square meter solar panel. Even at Earth's distance, we can still get a significant amount of energy from the sun. I don't know if any of you guys use solar panels on your house, but guess what that turns into once it makes it through the atmosphere? That's in space. After you travel through Earth's atmosphere, that number is reduced to about 400 watts per meter squared. That's what you get on the ground. So we basically lose 2/3 of that just due to absorption and scattering from our atmosphere. And by the way, there's no such thing as a 100% efficient solar panel. If you're getting 400 watts per square meter on the ground, a real solar panel that was 1 square meter big would probably only get about 200 of those watts, because most solar panels today have a 50% efficiency or something like that. But if you have many square meters on your roof and you cover your roof in solar panels, you get 200, 400, 600, 800. You could easily get thousands of watts worth of power, provided you live in a particularly sunny place in the country.
How far is I forget how far Mars is from the sun.
1.5 AU, 50% further.
Which one's closer? Next closest to the sun.
Mercury. So your idea is, what if we covered Mercury in solar panels? I mean, Mercury is just a dumb rock anyways, right?
Well, no, I was thinking like, okay, so if like Mercury's like half an AU.
0.4 technically.
Okay. Yeah. Okay. So that's kind of what I was thinking. So like, I would literally melt because I'm like pasty white, and I have a hard enough time here not looking like a lobster.
Right. On the surface of Mercury, let's think about how much brighter the sun is. Brightness falls off as 1 over the distance squared, right? So if you're 40% of an AU,
That's 6 times 10 to the 10th.
it's
No.
1 over 0.4 squared is roughly 6.3 times more light. So instead of 1400 watts per meter squared,
Oh yeah.
you'd get 9,000 watts per meter squared.
Holy crap! That's like having like
Being
a
cooked in an
bunch
oven.
of
Yeah,
a bunch of magnifying glasses just walking around you.
exactly. And by the way, the subsolar point of Mercury underneath the sun, it has an average temperature of 700 Kelvin. And I think that's hot enough to melt lead. Like lead would turn into a puddle on the surface of Mercury. Let's just change that to Fahrenheit quickly to get a sense of that. So we'll do 700 Kelvin to Fahrenheit. Oh, in Celsius. Oh, what the hell? I want Kelvin.
Oh, you did 700K Fahrenheit.
Oh, I see. 700 Kelvin is 800 degrees Fahrenheit. The surface rock of Mercury is 800 degrees.
That's 300 degrees higher than putting your oven on broil.
Right. Right. And imagine if you put your hand
Good
on the rock.
God.
I bet the rock on Mercury is almost like gooey and tacky. Like, you know how like in the summer times your driveway can have those little repair patches and they're kind of gooey. I bet the entire surface is gooey like that. Okay. So that's for Mercury, by the way.
That'd be like the effect of someone from here going to Arizona.
Yeah.
And looking at just the air.
Absolutely.
As you remember from being in Tucson, it just, you walk outside and
sorry, Joel, I gotta erase this. Okay, guys? All right, let's shift our gears for a second here. And let's talk about the different types of spectra that we find in nature. I told you guys that different sorts of things emit light. Examples were the sun, a light bulb. Enrique mentioned fire. I mentioned lightning or lightning bugs and neon signs. It turns out that when you analyze light with a prism or with a diffraction grating, you tend to see one of three types of spectra in nature. And this picture here is going to show you a little bit. Let's go to slide 64 first. This is a crappy little cartoon. Oh, look at Fenway. Fenway's bored. He's passed out. You see one of three different types of spectra in nature. When we looked at the matchstick together today, we saw a continuous spectrum. That's a complete rainbow with no breaks. In a lab that we do next week, I'll show you examples of emission line spectra. That's when you heat up gases like hydrogen or helium. And then there's a third type of spectrum called an absorption line spectrum. There was a famous Russian scientist, or a Prussian scientist, I should say, named Gustav Kirchhoff, who did experiments in the late 1800s on radiation. He basically made different things glow. And he analyzed why sometimes a thing would make a rainbow, why sometimes it would emit lines, and why sometimes he'd create an absorption spectrum. And he came up with a rule that is kind of explained by this cartoon. Why do you sometimes get a rainbow? Why do you sometimes get lines? And why do you sometimes get a rainbow with dark lines? I should also mention, class, that a tool that you would use to do this is a crappy version here. This is what is known as a spectroscope. It's a device for breaking light up into its component wavelengths. I actually might be able to hold this up here. Actually, let me do a little crappy demo with you guys. Sorry, I kind of have this really long extension cord, so. This is actually a 100-watt light bulb, so it ought to generate quite a bit of light for us. The cord was not long enough, so I had to get this overbearing extension cord. Ooh. Okay. I'm going to point the spectroscope to the lens of your camera. And I'm going to shine light into the slit. So I've got to get everything in just the right position. I can do this, but you just have to bear with me for a second. Oh. Can you guys see that spectrum there? What kind of spectrum are you seeing?
I'm seeing around 600, 500.
Yeah, but you're seeing colors at those wavelengths, right?
Yeah, I'm seeing colors. So I'm
The
seeing
point that I'm trying
red,
to make is
orange.
this is an
green.
example of what's called a continuous spectrum. It would look a lot cooler if you were doing it yourself instead of me holding it up to a camera. But you're basically seeing a complete rainbow there. It's a pure rainbow with no breaks. That's a continuous spectrum. It's possible for me to produce other types of spectrums, and I'm going to do a lab on this next week. Okay. Now, Gustav Kirchhoff came up with a number of rules of what types of glowing objects would create which types of spectra. And the three types of spectra are the ones, well, I just showed you an example of a continuous spectrum. But if I share screen here and I temporarily go back to hydrogen, hydrogen gas can produce this. This is a type of spectrum called an emission line spectrum. You don't see a rainbow, you see individual lines, a red line, a blue line, a purple line. And this type of spectrum down here is called an absorption line spectrum. That's where you get a rainbow, but there are certain key wavelengths that are removed from the spectrum. We call this an absorption line spectrum. Okay, I'd like to now introduce to you Kirchhoff's three laws of radiation. Okay. The first law is called the law of black bodies. And it goes like this. A hot, dense, solid produces a continuous spectrum. In the example of the light bulb, which we just looked at together, the hot, dense solid was in fact that metal filament that you can just barely see in there. That filament is a piece of solid metal, and that's what is glowing in the case of an incandescent light bulb. Because of this, we often call glowing pieces of metals black bodies. It's an old-fashioned term for hot, dense, glowy thing, okay? I could tell you the history of that some other time. Second law is called the law of emission. And that one goes like this. A hot, thin gas produces an emission line spectrum. The third law is the most confusing to explain sometimes. It's called the law of absorption. The law of absorption states a cold, thin gas in front of a black body produces an absorption line spectrum. These laws are important to us astronomers, because they explain how different types of matter produce different types of spectra. Because astronomers analyze light to learn about cool shit in space, we need to know these laws very well. In your labs next week, you'll see examples of all three of these types of spectra. I'm now going to teach you a couple of new formulas related to black bodies, but I'm guessing you guys need a minute here to get the notes. So take a second. Andrew and Cam, I guess, let me know when you're ready to move on.
I took a
I'm
picture
ready.
of it.
Okay, thanks, Cam. Yeah, that's a lot of words there. How you doing, Andrew?
I'm all done.
Oh, killer. Anyone else? Enrique, you good? All right, I'm erasing. Joel, you good? Okay.
Yeah, I'm good.
So I kind of want to zoom in on the black bodies for a second, okay? When I think of a black body, a black body is a hot, dense, Kirchhoff called it a solid, but I'm going to call it a thingy, because sometimes even gases can produce black bodies. Like, for instance, if you think about it, Enrique, when I lit this match on fire and we looked at it through a spectroscope, that fire, I said your name because you mentioned fire as a glowing object. Fire actually turns out to be a black body. So since the flame is made out of gas, it's not always a hot, dense solid, but sometimes it's just a hot, dense thingy. The idea behind black bodies is this. A black body glows due to temperature alone. And not chemical composition. In a sense, I'm going to be crude here. A flaming piece of dog poo would produce the same spectrum as a glowing filament of light, okay? If you set dog poo on fire, it will glow with a rainbow spectrum, just like a lamp does. And the only difference between the light puts out by the dog poo versus the light in the lamp will just be if there's any difference in temperature. But if you heat up dog poo to the exact same temperature of a tungsten filament, it will glow with the same exact rainbow spectrum.
I'll try it tonight and I'll let you know how it goes.
Yeah, okay. Joel's going to be out at the dog park with a lighter fluid.
Not.
My teacher told me to do this.
I have zero desire to do that.
Okay, all right. It's important to realize that black bodies produce a rainbow, and a rainbow is usually a form of white light. A black body usually produces white light, whitish light. And the white light is usually in the form of a rainbow if you break it apart with your spectrum. Remember that a rainbow is the same way of saying a continuous spectrum. I'm really trying to drive the idea home for you guys that things that are hot and dense produce light because of temperature. Can I show you what I think would be my ideal abstract sort of personification of a black body? If we were to look at a steel ingot
So
glowing in a
Brendan,
forge. Yeah.
with the flame coming off the matchstick, we're not actually seeing, like if we look at it through the spectrogram or whatever,
Yep.
we're not seeing the flame. We're seeing the results of the wood.
Careful, Joel. Can I say it a little better? I know what the question
Okay.
is. I need to say what you said better and more appropriately. The
Okay.
match creates a chemical reaction with the oxygen and the wood.
Right.
Basically, carbon and oxygen are creating a chemical reaction. That reaction is exothermic and it gives off heat. And the heat heats up the air so stupid much that the air itself begins to glow. So you're actually seeing glowing air that's been pumped full of heat. Now, air is not, you don't think that air is solid, but it turns out that air is dense enough that if you heat up air, it will glow just like this steel ingot. Believe it or not, air is dense enough where it actually behaves more like a solid than it does like a gas when it comes to glowing, okay? Which is a little bit awkward and weird. This is my concept of an ideal black body. It's dense, it's hot, and it's glowing. And it's glowing because you've heated it up, and it's only because of its temperature. Once again, if you analyze the rainbow that this produces, the rainbow will just kind of depend on how hot the metal is, okay? I want to show you a couple of graphs that try to explain this. I want you guys to imagine that I take this light and I pass it through a prism and I produce some white light. So let's take a look at that. So I pass the white light glowing from that thing into a prism and I produce a rainbow. The question I want to ask is this. If I scan along this spectrum with a light meter, will I discover more blue light or more purple light or more green light or more red light? Or will all the wavelengths come out the same? This graph is known as a black body spectrum profile, and I want to try to show you a picture of that. This graph here shows you what a black body spectrum profile looks like. So let's just take 4,000 Kelvin. This is roughly the temperature of the filament of light that we were just looking at in a light bulb. You will notice that if I graph, this is the brightness on this axis, and it's the brightness measured in watts. They say arbitrary units, but the units for our class for brightness are brightness in watts per meter squared. Here they're plotting the wavelength in microns, although it might have been nicer if they had plotted it for us in nanometers. You guys will recognize that this is, how many nanometers is purple light again? Let's see what you guys know.
400.
No, 100 is ultraviolet.
No, I said 400.
Oh, sorry, it was quiet. So this is 400 nanometers. And what about red light?
650.
We'll go with 700 because it's just easy, okay?
Okay.
You'll notice that there's a family of curves which depend upon temperature. But if we just analyze one of the curves, this would be the filament of a light bulb. You can see it's producing light across the entire electromagnetic spectrum. Not only is it pumping out visible light, but it's also pumping out light over here. What band is this, guys, just before violet?
UV.
It's pumping out ultraviolet light. And what's the one that comes after visible, right after red?
Infrared.
It's pumping out some infrared. And if you kept plotting, you'd even find a tiny amount of radio waves being produced as well. It turns out that black bodies produce light at all wavelengths of the electromagnetic spectrum. But I want you to notice something. It does not produce all the wavelengths equally. There's always one wavelength, which I'm going to call lambda max, which is a little bit brighter than all the others. In fact, let's just think about taking a hot, dense solid and making it glow and what that would look like. So here's your iron poker. It's a dense solid. And at first, at room temperature, it's cold, so it does not glow. Then you take the poker and you put it in the fire and you begin to heat it up. At first it glows a dull orange. Then it will become red hot, like a red hot poker. And if you kept heating it up in your fireplace, eventually you would discover it would glow pure white. That's the temperature that's increasing. You can't get this poker much hotter in a backyard fireplace, but in a foundry you could use a blast furnace and you continue to heat this up. You would eventually discover that the metal would glow blue if you could make it hotter and hotter and hotter. I want to explain that here on the board using two formulas. I need to erase though.
I'm not done.
All right, let me know when you are. I've just got these two formulas to introduce and then we can stop and we'll be ready for our homework. How are we doing, Andy?
All done.
All right. Okay, here we go, class. As I heat a black body, I get two effects that happen simultaneously. The first effect is like this. More temperature equals more overall light produced at all wavelengths. The second effect is that more temperature produces what I am going to call bluer light, light that goes from red to white to blue. Where I think I just made up a word called bluer. There are two formulas that explain these two effects, and that's what we need for our homeworks today. The one that explains more temperature equals more light is called the Stefan-Boltzmann law. And the Stefan-Boltzmann law goes like this. Brightness equals the Stefan-Boltzmann constant. Now, that letter that you see there, that's the Greek letter sigma. Just draw an O and put a little hat on the top of it. It's the Stefan-Boltzmann constant times temperature to the fourth power, which means the amount of light that I get from a glowing object grows as T to the fourth power. That's a lot of change in light for a small change in temperature. This constant is known as the Stefan-Boltzmann constant. It's a crazy number from physics that I cannot explain to you because it's above your pay grade, but I'll tell you what the constant is equal to. 6 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth. That's just a dumb number for you right now. Okay, we'll try an example to see how this is used in just a moment. The second formula, more temperature equals more light, is known as Wien's law, or if we pronounce it as the Germans might have, Wien's law, okay? And Wien's law tells us that the maximum wavelength produced by a black body is approximately 3 million nanometer kelvins divided by the temperature T. We really ought to try a quick sample problem with this. Let me know when you're done copying. I'm going to give you guys a break in just a minute here. Just power through to the very end with me.
I'm all done.
Enrique, you good? Cam? All right. It's no good introducing a formula unless I show you how to use it. Okay. Here's a light bulb. It has a filament. Usually it's made of a metal called tungsten. A tungsten filament has a temperature of 3,500 Kelvin. No kidding, those things are pretty damn hot. Of course, that tungsten filament is going to glow with white light. We are going to analyze the light. We're going to ask question 1. How much light does it emit? Question 2 will ask, what is the peak wavelength of light emitted? I'm going to punch you through this kind of quickly here. Answer 1, we're going to use the Stefan-Boltzmann law for. Brightness is sigma times T to the 4th power. That tells you how much light based on the temperature, which is 6 times 10 to the minus 8. The units are watts per meter squared per Kelvin to the 4th times 3,500 Kelvin to the 4th power. I want you guys to punch this with me because some of you don't know how to do a 4th power thing. Let's empower you to take the 4th power. Okay, follow with me. 6 exp minus key 8 times 3,500. Okay, here we go to the 4th power. Do you see this key here, x to the power of y? Hit that.
Yeah.
Raise to the power of 4 equals. Now let's count the zeros. 1, 2, 3, 4, 5, 6. That's 9 times 10 to the 6, or 9 million watts per square meter. That's the answer to question 1. The filament produces a brightness of 9 million watts per square meter. Let's try answer number 2. We're going to use Wien's law for this one. Lambda max is 3 million nanometer kelvins over 3,500 Kelvin. If I plug that in, 3 million divided by 3,500, I get 860 nanometers. Because kelvins cancel out. Class, in what regime of the electromagnetic spectrum is 860 nanometer light? What type of light is that? Sorry?
Infrared. Infrared.
Infrared, very good. Do you want to know why these light bulbs are so sucky? You design a light bulb to emit visible light so you can see in the dark and not stub your toe. But these things actually produce more infrared light than they do visible light. which is a waste of energy. This light bulb might be 60 watts, but about 60% of those 60 watts are going into the infrared where you can't even see it. This is why LED light bulbs are so much better. LED light bulbs do not make black body light. They use emission to make light. So you can produce an equivalent amount of white light with way less wattage. Oftentimes you'll see at Home Depot that 60 watt incandescent bulb is equivalent to like 20 watt or maybe even a 15 watt LED bulb. That's because when you're using incandescent lights, when you're using black body light, you don't just produce the light in the visible spectrum. So this is the amount the light bulb produces in the visible spectrum. But most of that wattage is totally getting dumped into the infrared, which does you absolutely no good. It heats up your house. So in the summertime, that's actually not advantageous. Okay, let's leave it there. We're going to take a little tea break, a little pause for 15 minutes. I'm going to relax and eat a sandwich. And then when we come back, we're going to do homework 6. Sound like a plan, gang? We love tea break, right?
Yes.
Okay. All right, then I will pause the recording. Okay, Astronomy 1010, welcome back. We're going to embark on homework number 6, more on radiation and light. Let's get those numbers up, and here, let's do the thing that we need to do. Let's hide the trolls. That comes first. Then we will go to speaker view. And while I'm doing the erasing, I want you guys to look up the numbers for me. There's 2 different chapters here.
Jake, you look like you're still trying to take the midterm. You all right? You recover yet?
I did. Yeah, I was trying to look at the homework.
Oh.
I was about to say, I'm closing that out the second this homework ends.
Oh no.
All right, let's get our names on the page. Homework number 6. We should have this is AS1010. Chapter 5, we got some questions, and chapter 6, we got some questions. What are the numbers?
So chapter 5, it's 56, 58, 59.
Okay.
And then chapter 6 is 52 and 54.
All right. Joel, why don't you take us out here with chapter 5, number 56.
All right. X-ray photon. What is the wavelength of an X-ray photon with the energy of 10,000 electric volts?
So we can say
10 keV.
keV. Of course, is 10,000.
Yeah.
EV.
What is the frequency? And one EV equals 1.6 times 10 to the 19th joule.
Negative 19.
Oh, yeah.
That's kind of important. An electron volt is a tiny packet of energy. We usually express the energies of photons in electron volts because the energies are much smaller than everyday life stuff. Okay, what are our formulas? Let's start with either frequency or wavelength. You guys choose. I slapped those formulas up on the board at the beginning of class. Hey, Gabby, nice to see you. Do you guys know what to do? Take out your formula sheet, or I guess we discovered that your formula sheet did not actually have these equations on them.
Oh, I know it. Hold on. what is that? Is that C equals what is that?
Wavelength times frequency. It's lambda.
Yeah, lambda times F. And then E equals H times F. And then E equals H times C over lambda.
Exactly. Which one should we use to find the wavelength? I call this equation 1. I call this equation 2. And I call that equation 3.
We have E.
We have E.
I would say 2, because we have E and H is a given.
Okay.
And we need to find the frequency.
Okay, so you want to do this first. That's fine. Let's do the frequency. So if energy is H times frequency, frequency is E divided by H. Oh, we got to do some unit conversions, don't we? Remember that H, Planck's constant, is 7 times 10 to the minus 34 joule seconds. So what happens if we put 10,000 EV up there? EV does not cancel with joules. So what do you guys think?
Yeah. So you have to do 10,000 EV times the division bar.
Let's put the dimensional analysis right in the problem, okay?
Okay. And then 1 EV on the bottom, joules on top. So 1 would be on the bottom, and 1.6 times 10 to the negative 19.
Okay, punch them up. Do you guys know how to punch something like this into your calculators? This times that divided by that.
Is it 2.3 times 10 to the 18 seconds?
Not seconds. Not seconds.
Oh, I forgot. Hertz?
It is hertz, but look, seconds, Bella, is on the bottom of the equation. So it's per second. Per seconds are hertz. You see the difference?
Yes.
When seconds is on the bottom, it's not the same as normal seconds. Okay, what do you want to do next? We got to get the wavelength. What to do?
I would use 1.
Huh?
I would use 1.
Okay. So if C is equal to wavelength times frequency,
So you do wavelength equals C over F.
Okay. I happen to remember C, 3 times 10 to the 8 meters per second. Divided by the frequency, 2.3 times 10 to the 18. I'm going to write this as 1 over seconds rather than hertz. That way my units cancel nice. All right, punch them up. One times 10 to the minus 10, probably.
-1.3 to the minus 10.
Oh, right, because 3 divided by 0.3 will be 333. So 1.3 times 10 to the minus 10. What are my units, Jake? If that was you.
Oh, it wasn't.
Oh, it sounded like you.
Would it just be meters? Because
Yeah.
the second cancel out.
Correct, it's just meters. How many nanometers is that? That's, 10 to the minus 10 meters. Those are units called angstroms. Angstrom is an old-fashioned spectroscopy unit. You'll be using that in your lab next time.
Would that be 13?
No, if I make it 13, it's 10 to the minus 11. If you want to make it 10 to the minus 9, it's 0.
Oh, yeah. Because it's negative. I have to move it the other way.
Remember, the cutoff for X-ray is right around 1/10 of a nanometer. So it goes 10 to 100th of a nanometer.
What is it? What is the bottom 0.313? I can't see that. Right under.
Nanometers.
All right.
Okay, that takes care of question 56. Let me know when I can erase here. Okay, I'm erasing. Jake, you're next in my Hollywood Squares. Will you read chapter 5, number 58, please?
Yeah. 58, thermal radiation laws. A, find the emitted power per square meter and wavelength of peak intensity for a 3000 K object that emits thermal radiation.
Jake, let me pause for a second. I speak astronomer physics code. When they say thermal radiation, they mean black body radiation. And remember, they want us to find the power per square meter, which means find the brightness. Honestly, saying power per square meter is a really shitty way to talk. Only an asshole would say that. You should say brightness, or you should say watts per meter squared. Power per meter squared is mixing and matching your metaphors there. I don't like it. Find the brightness, and they also want us to find the lambda max, the peak wavelength. These are the two formulas that you learned at the end of our lecture today, just before tea break. You'll remember this is the Stefan-Boltzmann law, and this is Wien's law. Let's write that down because you all are still learning, and you need to learn. Okay. For part A, what did they say? Jake, again?
Find the emitted power per square meter and wavelength of peak intensity for a 3000 K object that emits thermal radiation.
Very similar to the sample problem that we did at 3500 K. First, we'll find the brightness. Brightness is sigma T to the 4th power. The Stefan-Boltzmann constant is 6 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th, multiplied by 3000 Kelvin to the power of 4. Punch that up, kids. Punch it up. Do your duty.
I got an answer.
Okay, what is your answer?
After I like rounded, I got 4.9 times 10 to the 6th.
Good. And what are the units, Jake?
Units would be watts per meter squared.
Nicely done, sir. And that makes sense because we got about 6 million.
Brandon, can
Yeah,
you show me how to do the square 4 again?
yeah. Say 4th power, okay?
4th power, sorry.
Although I like square 4, that's pretty cool. Yeah. So remember that the 4th power is this raises to the power, x to the y. For instance, 2 to the power of 4 is 16. This problem, we should do 6 exp negative 8 times 3000 to the power of 4.
Okay, I see what I did wrong.
Okay, good, good. Don't do that no more. We also have to find the peak wavelength of emission for each problem. So this is the brightness. I'm sorry?
Wait, for that one, it would come out to 486.
And we rounded the 86 to 90 cents.
All right, I know what I did wrong. I forgot the 4.
Oh, okay. And now we'll do Wien's law. Lambda max is 3 million nanometer kelvins divided by 3000 Kelvin. That's easy enough. What do you get?
$3,000? No, 1,000.
What are the units?
Or nanometers.
What type of light is that? That's the same as 1 micrometer, or astronomers call them microns. 1,000 nanometers is 1 micron. In what regime of the infrared?
So what is that? Oh, what is the MM? Is that just MM?
Plus,
Thanks. NM means nanometers. A nanometer is a billionth of a meter. A micron is a millionth of a meter. So 1,000 billionths is 1 millionth. How many nanometers is that? I just want to see if you guys can get good at the metric system. That would be kind of cool. How many millimeters is that? A millimeter is 1,000th of a meter. Okay, well, think about it. Can I erase? I'm going to save myself some time here. For part B, we're just going to have a new temperature. Jake, what's the temperature for part B?
Part B is 50,000 kelvins.
Okay. 50,000. Second verse, same as the first. Tell me the brightness, class. And tell me the peak wavelength. Punching is a U job.
I got 3.75 to times 10 to the 11.
So 3.8.
Oh yeah, sorry.
That's okay. I like to keep it to 2 sig figs. How about your wavelength, your peak wavelength? Well,
7.6 times 6 times 10 to the 6.
no way. 3 million divided by 50,000
Oh
cannot.
no, I did it wrong.
Yeah.
60?
60 is correct. Hold on a sec. I'm wrapping a wire because you guys are taking too long.
You just start knocking zeros off and then divide it.
Say that again.
You just knock zeros off. You knock 4 zeros off the 3 times 10 to the 6, and then
30.
you're left with 300 or 300 divided by 5.
Exactly. Exactly, Joel. 60 nanometers. What regime of the electromagnetic spectrum is 60 nanometer light?
Oh God, I need to space this out.
The one to the left of ultraviolet.
Damn it,
Okay.
I don't have an eraser.
Was I right?
Yes. Yes. Ultraviolet.
Oh,
See, you said something weird. You said the one to the left of ultraviolet. But I think what you meant is the one to the left of ... visible, which is ultraviolet. The one to the left of ultraviolet.
I can't remember the increment. So
UV goes from 400 nanometers down to 10 nanometers. So this is getting close to X-ray, but it's not quite there.
Okay.
I'd like to erase.
I'm not done yet.
Let me know when you are.
All right. I'm all set.
All right. 2 down, 3 to go, guys. This one ain't so bad. 2 down, 3 to go. Hey, Gabby, are you down to read a problem? It'd be nice to hear your voice. Chapter 559, what do you think?
All right. Says hotter sun. Suppose the surface temperature of the sun were about 12,000 K rather than 6,000 K.
Okay.
Part A is how much more thermal radiation would the sun emit?
And when they say radiation, they don't mean particle radiation, they mean light. How much more light does the sun emit? Okay, let's pause there, Gabby. Do you guys know which formula we want to use to answer this question? Which formula do we need to answer the question? Yes, Matt, the Stefan Boltzmann law. Now, Matt, I can think of 2 ways to do this. Let's look at the Stefan Boltzmann law together. We can plug in for 12,000 and get a 1 brightness. Then we can plug in for 6,000 and get another brightness, and then we can take the ratio. That will tell us how much more radiation. Or we could do it algebraically and divide first. Which do you guys like best? If we do it algebraically, we'll cancel out terms and plug in the temperatures at the end. Jake, what do you say?
Doesn't really matter to me.
See, it kind of matters to me, but I want you guys to pick the right choice. I want you to choose. What's the right choice?
If it was me, I would do the ratios because you don't really need the constant.
Yes, you're right, Joel, and that is the right choice. Thank you. So what we're going to do is we're going to take the ratio of the 2 brightnesses beforehand. We'll take the ratio of the brightness at 12,000 Kelvin. We'll divide it by the ratio of the brightness at 6,000 Kelvin. And what we'll get is on the top, we'll get sigma to the 4th at 12,000 over sigma to the 4th at 6,000. As Joel points out, the Stefan Boltzmann constants will cancel out. Hey, Joel, I want to show you one other slick move. Rather than just plugging in the temperatures, I'm going to factor out the 4th power. That's a slick Rick algebra trick, okay? Slick Rick algebra trick. I'll take the ratio of the temperatures at 12 to 6, and I'll raise that all to the 4th power. So when I plug in my values, what will the ratio of temperatures turn out to be?
Just T12 to T6.
Yeah. And T12 is, all right, maybe you guys needed a little more literal. I think I was getting too abstract on you. Let's be a little more literal. Let's plug in the temperatures, 12,000 Kelvin divided by 6,000 Kelvin. Okay. So now tell me, what is 12,000 divided by 6,000?
2.
What is 2 to the power of 4?
16.
What is the meaning of the 16?
It would be 16 times more light.
Exactly.
Hey, I got it. I struggled
Yeah.
with this in the summer.
I'm going to phrase it like they did, 16 times more radiation. That's part A. Let's let everyone catch up before Gabby reads again. Andy, how we doing?
I'm still copying. I'm done.
Hi. Gabby, what's part B?
Part B is what would happen to the sun's wavelength of peak emission?
You guys remember what formula we need there, right?
Weens.
Right. Guys, unlike what we did last time, I think we should plug it in twice and see how the wavelength changes. The actual wavelengths are kind of interesting. So let's first do lambda max at 12,000 Kelvin. What is 3 million divided by 12,000?
150.
Try again.
250.
Pardon?
I got 250.
250 sounds right. What are the units?
Hold on. It's going to be nanometers.
What type of light is
Okay.
that? What type of light is 250 nanometers?
It's still ultraviolet.
Very good, Jake. Let's do the normal sun. 3 million nanometer kelvins. The surface temperature of the sun is 5,800 Kelvin. Or I guess they say 6,000. So let's just do 6,000.
Be 500, right?
Yeah. What type of light is that?
Is that still ultraviolet?
No. Not at all.
Is that infrared?
No. Not at all.
Oh, is that visible?
Yeah, what color?
Oh, 500.
Blue.
Blue.
I guess it's kind of teal.
Is that cyan?
Yeah, I mean, I guess this is cyan. 500
Okay.
is, I'd say it's either green or teal.
Okay.
This is like the Stroop test because I'm writing it in red. Do you guys know about the Stroop test? The Stroop test is this psychological test where they first let people read the names of colors Like it'll all be printed in black, blue, red, yellow, green, orange. And it takes people like a fraction of a second to read the names. But then they have the same words printed again, but all the colors are fucked up. So they'll write the word blue, but they'll make it red. And they'll write the word red and they'll make it green. And it slows people's reaction times down. Like you have a harder time reading the name of the word. And you can try it yourself. This is totally off topic, by the way. So I'm just wasting everyone's time, including my own. But you should look up the Stroop test from psychology. It's kind of interesting. Yeah. So you just try to read all these words and you get all messed up. It's hilarious, right? Like blue, red, green, blue. It actually slows your reaction time. Anyways, 500 is kind of teal. There's a part C, isn't there, Gabby? Let's wait until Andrew's done. Andrew, are you done?
Yeah, I'm done.
I'm erasing. What's part C say?
Well, did we answer part B?
Yeah, the new wavelength is half of the old wavelength. It's ultraviolet instead of infrared. Oh, sorry, ultraviolet instead of visible. Okay, fine. Okay, so the new wavelength is half the old wavelength.
Do you think it would still be possible for life to exist on Earth and explain?
Let's look at the answer to part A and the answer to part B. In part A, we learned there's 16 times more radiation. And in part B, we learned that the new peak was in the ultraviolet. So I want you guys to first imagine the sun was 16 times brighter in the sky. And now I want you to imagine that most of that light was peaking in the UV. You know what UV light does to you, right? What's the number one effect of UV light on humans?
Sunburn.
Exactly, Jake. So if you had 16 times more UV light at the beach, would that be good for you?
We'd be dead.
We'd
Yes.
definitely be dead. It would break, no, it would break down the cell walls of your body. So what's the answer to part C?
Life couldn't exist.
Well, you'd think so, but you know what the thing is, Jake? Life is kind of badass and it's kind of hardy. Now, I don't mean that you or me are badass and hardy. We're probably kind of wimps, but some types of life, like for instance, the tardigrade, you know what those are? No?
Is that like the mini bear looking thing?
Yeah. And they find these things in pond scum. They're all over the place. So they did this experiment with these look like fucking things out of your nightmare. It's pretty awesome. So these little microscopic organisms are smaller.
Looks like a manatee.
Yeah. They call them water bears. And they're only about a micron across, about 1,000 nanometers.
Creepy.
They took these things up to the International Space Station. They put them into the vacuum of space, where not only did they dry out from lack of air and water, but they were also irradiated with shitloads of ultraviolet light. Because once you're above the atmosphere, Jake, remember how like we saw that we went from 1,400 watts to 400 watts? The sunburn you would get in outer space would be way worse. So these things were irradiated with ultraviolet light while in a vacuum. They brought them back into the ISS and put them back in the water, and about half of them survived. So these things are pretty freaking gnarly. Most life probably could not exist, including plant life. But these little bastards, they're tough as nails. They might make it. I don't know. So let's answer the question by saying most types of life could not exist under these conditions.
So when I asked you about going to, was that Venus or Mercury? That's kind of the effect.
Yeah, you would get more radiation and you would get more ultraviolet light just because, well, see, the thing about raising the temperature is it would be different in, it's different in some ways. You can see that when you raise the temperature of an object, not only do you get more light, shoot, what was that, 60? When you raise the temperature of an object, not only do you get more light, but the peak wavelength starts to shift towards the ultraviolet. However, if you went to Mercury, you would just get more light. The sun's peak is somewhere in the teal spectrum. So the peak wavelength would still be teal, but you just get more light. You'd still be operating under this black body curve though, because the temperature of the sun wouldn't change. So if the temperature of the sun changed, it'd be doubly bad because not only do you get more light, but you get more of the light in the peak of the UV. You know what I mean? If you went to Mercury, the peak would still be in teal, but because you're getting more light, you'd end up with more ultraviolet light as well. Most could not survive 16 times more light leaking in the UV. At a certain flux, ultraviolet photons will break down cell parts and just reduce you to a rubble of atoms and molecules.
Sounds like a blast.
Or a zap or something. All right, 3 down, 2 to go. Cam, can you read us chapter 652?
Sorry, my mic was muted.
That's okay.
Finding planets. Suppose you were looking at our own solar system from a distance of 10 light years. So question A asks, what angular resolution would you need to see the sun and Jupiter as distant points of light?
Okay. To answer this question, we are going to use the small angle formula part 2, which solves for angular separation in arc seconds. The angular separation in arc seconds is 206.265 arc seconds times the separation divided by the distance. This is basically a version of the small angle formula from chapter 2, but solved for arc seconds. So in the picture, we have an eyeball, and we're going to be looking at, well, the sun and Jupiter as distinct points of light. So first we'll have the sun, and then down here we'll have Jupiter. And Jupiter will be separated by some angle from the sun. I'm going to do you guys a solid. I'm going to tell you that the separation between Jupiter and the sun is about 5 astronomical units. And this distance here is 10 light years away. Class, I'd like to point out that S and D, they need to have the same units in order for this formula to work. They currently do not have the same units because this is the D and this is the S. I suggest we convert 10 light years into astronomical units. Cam, that's your job. Help me use dimensional analysis to convert 10 light years into astronomical units. You will need 2 steps. Oh, it might be helpful to know that 1 light year is 9.5 trillion kilometers. Cam, how do I do it?
So you use 4 steps of dimensional analysis.
Yes, correct.
So step 1 is to write down the number to convert with its units.
All right, so what should I write down?
Let's see. I think you write down 206,265.
Nope, that's not what we're trying to convert. The 206,265 is cool. The issue that you have right now is that S and D have different units. Your S has units AU. Your D has units.
Oh, I can read that was a 5.
Sorry, that's an S.
Yeah, it looked like an S.
No.
So you would do 9.5 times 10 to the 12th power?
That's not what we're trying to convert. What are we trying to convert? What should I do, guys?
Oh, no.
10 light years.
10 light years, Cam, is what we're trying to convert.
All right, all right.
Now what?
You multiply.
Now what?
9.5 times 10.
No, you're not allowed to give me any numbers, Cam, until your units are in place. Dimensional means units first, numbers second.
Kilometers in AU?
Well, you got to get rid of light years first.
Oh, okay. So light years would be at the bottom.
Right. And what's going to be on the top?
Kilometers?
Yes. Then you have to do another division bar. What units go to the next one?
So I know the bottom one is kilometers.
Yep.
And I think the top is AU.
That's right. Very good. All right, now let's put in our conversion factors.
So the top for the kilometers on top, it would be 9.5 times 10 to the 12th power.
Correct. What goes in the bottom?
1.
Correct. How about AUs to kilometers?
So for the bottom, it's the same thing as the one on the other one, 9.5 times 10 to the 12th. And
No. That's the number of kilometers in a light year. But we need the number of kilometers in 1 AU.
So 5 for AU?
Nope. Look at your formula sheet for the conversion from kilometers to AU, or from AU to kilometers.
Okay.
Here's my eraser.
Should have it somewhere.
Anyone?
I know. So it's 1/1,000 kilometers.
False.
1 AU equals 150 times 10 to the 6th.
100.
Okay.
Okay. So how many? Punch them up, guys. Tell me what you get. 2 sig figs.
6.3 times 10 to the negative 56.
Definitely not.
10 times.
6.3 times 10 to the 5.
You only need scientific notation if it's bigger than a million.
Okay.
Your number is not bigger than a million. So how do I say that in plain English?
63,000 or
Oh.
63,333.
6.3 times 10 to something. I don't know.
No, you don't.
630,000.
Thank you. Someone speaks scientific notation. Units?
AU.
Kilometer? Oh, AU.
That's what 10 light years is. All right, we're ready to plug this into the small angle formula part 2. I'm going to do that up here. So for part A, for Jupiter, ten light years is the distance, which is 63,000 AU. That's your D. Your S is 5 AU. Alpha is 206,265 arc seconds times 5 AU over 630 AU. Punch him up.
Brendan.
Yeah? Read it out to me, Joel. 2 sig figs.
I was trying to wait for other people, but
Oh, okay. It's okay, Joel. Just tell us.
okay. 2 sig figs.
Yes, please.
1.6
1.6 what?
arc seconds.
Cam, what's next? Why don't you finish up first and then read part B once you're finished?
Okay, so part B asks, what angular resolution would you need to see the sun and Earth as distant points of light?
Now, Earth is even closer to the sun. Earth is like over here. And Earth is only 1 AU from the sun. So it's going to be an even smaller angle this time. In fact, I suspect it's going to be 1/5 that angle. It's still 10 light years away, but now the separation is only 1 AU. So for part B, for Earth, the separation is only 1 AU. So you get 206,265 arc seconds times 1 AU over 630,000 AU. Let me know what you get.
I got
You got what?
Would it be 33?
Not 33.
I got 0.33 arc seconds.
Good. That's what I'm
Oh.
here. Cam, once you're done with that, read part C.
Oh, I'm already ready. I'll just wait for someone. Okay. So question C asks, how do the angular resolutions you found in parts A and B compare to the angular resolution of the Hubble Space Telescope? Comment on the challenge of making images of planets around other stars.
Okay, so the question is basically asking, not can, but it's asking, could Hubble resolve these planets? Now, Hubble's minimum angle of resolution is due to diffraction. If Hubble sees a minimum angle, they tell us in the text, of 0.05 arc seconds. Could Hubble resolve these planets at 10 light years? Could Hubble resolve these planets at a distance of 10 light years if Hubble sees a minimum angle of 0.05 arc seconds? What do you guys think the answer to that question is?
I think yes.
You are correct. Why is that?
Because the minimum angle is so small, like the angles we just computed were bigger than that, so it definitely would be able to see those.
Is less than 1.3 arc seconds and 0.3 arc seconds. Very good. That means, Jake, if you think about it, if there's a solar system 10 light years away, Hubble should be able to see a planet like Earth or a planet like Jupiter. But there's an actual problem with why. So you could say to me then, well, Brendan, where the F are my pictures of extrasolar planets? Because I want them. Let me show you one of the challenges of actually trying to image planets outside of our solar system. One of the only pictures we have of an exosolar planet is a planet that's so big that it actually gives off a significant amount of light. So I just want to go to the Wikipedia page on exosolar planets and see if I can find this image. This was the first time we ever imaged a planet around another star. It's HIP 65426b. And the planet is it's more massive than Jupiter, and it actually shines in the infrared significantly. This is something called a coronagraph or a stellar blockage graph. They take a black disk and they block out the light from the star, and you can see the so-called planet. In reality, this planet is actually giving off more light. It's almost like a star-like planet. The problem is Hubble might be able to resolve them at 2 to 1 arc seconds apart. But oftentimes the light from the star is so bright that it just completely overwhelms the planet. And you can even see this, let's see, like here. Here's another coronagraph showing AB Pictoris. That's another exosolar planet. The light from the star is threatening to outshine this thing. We even see this in that famous Carl Sagan image called Pale Blue Dot. Pale Blue Dot is a picture that Cassini took where you could actually see the Earth next to Saturn. But Saturn is so damned bright. Let's see if I can find the full picture here. The light from Saturn is so bright that it practically outshines the Earth. There's the rings of Saturn. It's not very easy to see. So you can just barely see the Earth there as a tiny dot. So the idea behind this problem is you would think it's a question of angle, why we can't resolve these planets, but it's really actually a question of brightness. So
You're out of focus.
You're low quality.
Okay, it's better.
On my thing here. Let me get rid of those pictures. What's happening is the extra internet is messing up your quality. So let me get rid of some of this stuff. That ought to help. In theory, Hubble can resolve the planets. But in practice, the dim reflected light of planets gets washed out by the much brighter star. So really the challenge in imaging planets is not just one of resolution and angle, but it's also one of brightness and quantity of light. My brain is dehydrated and it's angry with me, but we've still managed to get through 4 out of 5 problems. Andrew, when you're done, we'll have you read chapter 6, number 54.
I'm done.
All right.
So chapter 6, 54. All right. So the size of radio telescopes. What is the diffraction limit of a 100-meter radio telescope observing radio waves with a wavelength of 21 centimeters? Compare this to diffraction limit of the Hubble Space Telescope for visible light. Use your results to explain why, to be useful, radio scopes must be much larger than optical scopes.
Let's draw a picture of that Effelsberg radio telescope. That also has a dish diameter of 100 meters. So a radio telescope will have some support struts. It'll have some large radio dish. And then usually what happens is they have something called a feed horn antenna. And the radio waves from space, they come in, they reflect off the metal dish of the radio telescope, and they are captured by that feed horn. They bounce in, and that's the focus point of the dish. And the wavelength here is 21 centimeters, which is in the radio regime of the spectrum. Now, the limit to what a telescope can see is based on a property of light called diffraction. I'll have to cover that next time. And the so-called diffraction limit of any telescope, whether it's a radio telescope or not, it tells me that the minimum angle my telescope can resolve is 250,000 arc seconds times the wavelength of observation divided by the diameter of the dish. Here, the wavelength and the dish diameter need to have the same units. So I'll do a hasty conversion here. 21 centimeters. Do you guys know how many centimeters are in a meter?
100.
Thank you. So it's 100 centimeters to 1 meter. What do you get if you divide 21 by 100?
0.21.
0.21. So the diffraction limit of a radio telescope, the minimum angle, would be 250,000 arc seconds times 0.21 meters divided by 100 meters. Punch that up. Jake, what did you get?
I got 525
525 what?
arc seconds.
Very good. Is that a good or a bad resolution, Jake? I'm just going to say 530 arc seconds. Hey, Jake, how many arc minutes is that? Divide by 60 to find out the number of arc minutes.
Oh, divide by 5. Okay. 8.8.
So about 9 arc minutes. What's the angular size of the moon?
0.5
0.5 what?
arc seconds.
False.
Oh, AU.
No, that's not an angle. The angular size of the moon is an angle.
Oh. I don't know. I need to phone a friend.
Degree.
0.5 degrees.
Oh.
How many arc minutes across is the moon? Wow.
This is a trick question.
You failed me. You guys have failed me as students. I thought I taught you things. I thought we could have an intelligent conversation. You can't tell me how many arc minutes in angular size the moon is? Jake just said it was a half a degree. How many arc minutes is half a degree?
30.
30. So if the moon is 30 arc minutes across, but my telescope can only see an angle of 9 arc minutes, what would the moon look like through the Effelsberg radio telescope?
Ginormous.
No, it would be 3 pixels across. This is what the moon would look like through a radio telescope. It would only be 3 pixels tall and 3 pixels wide. It would look like a piece of poo. Okay? It would look like that's the, if you took a picture with your everyday camera, it would probably be 1,000 pixels across or something. Because each pixel is only sampling a third of the moon. Do you see what I'm saying? In other words, this resolution is sucky. It's wicked sucky. Let me put it in simple terms for you. Wicked sucky angular resolution. In fact, let's calculate how many times worse than Hubble it is, because they asked us to do that. If you compare 530 arc seconds by 0.05 arc seconds, which is Hubble, what number do you get?
26 and a half.
Huh?
26 and a half.
No.
Oh, no, wait. No, sorry.
Just punch it up.
10,600.
11,000 times worse than Hubble. There's another part to this question, Andrew. What was the other part to the question? Well, first finish copying and then read it.
Right. Let's see. Use your results to explain why, to be useful, radio telescopes must be larger than optical telescopes.
Why are them radio telescopes so big? Do you guys know about the Arecibo one in Puerto Rico?
I know about it. It was in the movie.
Until recently, it was in a James Bond movie. I think they blew it up. Until recently, one of the Arecibo telescope, one of the largest radio telescopes in the world, is 1,000 feet in diameter or 300 meters in diameter. It's so big that they just poured it into a mountain valley in Puerto Rico, and you can't really point the telescope. You have to wait for Earth to rotate into the direction of the object that you want to look at. Why did they try to make this so big? What was their motivation to create such a stupid, huge telescope? And what's it got to do with the diffraction limit? And what's it got to do with this sucky 9 arc minute resolution?
To get as complete a picture as possible.
Well, obviously you want the smallest angle as possible so you can get fine detail. When you say complete, that it's not about completeness, it's about detail.
Well, yeah, like with that 100 meter, you just get pixels. Like with the 1,000 meter, you get
53 arc seconds. Right?
Get a lot, yeah.
So in other words, wavelength go up, angle get bad. Diameter go up, angle get good. You see what I'm saying? Because minimum angle is inversely proportional to the diameter of your dish. If you're operating at long ass wavelengths like 21 centimeter radiation, well, that's going to make a sucky angle. So you got to make your dish big to compensate for it. Let's put that into terms here. Radio telescopes operate at longer wavelengths and thus suckier resolution. By increasing the diameter of the dish, you lower the diffraction limit angle, underline diffraction limit because that's what it's called. I made the point of specifying that it's an angle to remind you guys of that. You lower the diffraction limit angle and thus improve image resolution. You obviously want to be able to see the tiniest angle possible. to get the most detail from your picture.
That was what I was trying to say.
Okay. Well, it can be hard to figure out how to say these things properly,
Yeah.
which is the art of why it's good to do a little writing too, to sort of to help you learn how to talk about this stuff. And that, my friends, concludes homework number 6. Yay. Okay, it's margarita time.
Brandon,
Yes.
so the last bit says improve image resolutions. Okay. Thank you.
Sure. Cam, Andrew, how you guys doing?
I'm all done.
Cool. That's happy. So guys, unfortunately, actually, I just realized it's not margarita time because I have to do your midterm grades. Wah, that's not going to be fun. I'll try to get them up by tonight if I can. Oh, I need to get them up by tonight. So look for those midterm grades. They probably take a day to roll over, but CCRI will have them posted on Pipeline or My CCRI or whatever it's called. All right. Anything else from you guys? Okay, I'm stopping the recording.